Welcome to day 29 of our STL course. Today we are going to explore two advanced but essential concepts in the standard template library, function objects and predicates. These powerful tools will allow you to have finer control over STL algorithms, making your code more efficient and flexible. By the end of this session, you will learn how to define custom function objects, also known as functors, how to use predicates for algorithm customization, and the benefits they bring to your programming toolkit. Here are the objectives we will cover in today's session. We will start by defining function objects and exploring their syntax. Next, we will delve into the powerful built-in function objects that come with the functional header in C++. After that, we will focus on creating custom functors both with and without state so you can define your own logic in algorithms. We will also explain how function objects differ from function pointers and lambdas and when it's best to use each of them. Lastly, we will explore how predicates are used in STL algorithms to filter, compare, and transform data. Let's begin by understanding what a function object is. A function object or functor is simply an object of a class or struct that overloads the operator. This gives the object the ability to behave like a function, making it callable with the bracket syntax. Unlike regular functions, function objects can store state and contain multiple methods. This compatibility gives them a distinct advantage, especially when you need to encapsulate behavior with internal state. For example, the square struct you see on this slide overloads operator to compute the square of an integer, which means it can be used as a callable function in your program. So why would you use function objects in your C++ code? The primary reasons are flexibility, reusability, and performance. Functors can store state. This means they can keep track of data across multiple calls, unlike regular functions. For example, you can create a functor that counts how many elements satisfy a certain condition. Functors are reusable, which means once you define them, you can use them across various algorithms. Another important point is that functors are more optimized by the compiler, especially when used in STL algorithms, leading to better performance. Overall, functors are more object-oriented way to introduce function-like behavior into your code. The C++ standard library provides a variety of built-in function objects in the functional header, and these can be used in your algorithms immediately. Examples include plus, minus, greater, less, and more. These are template-based, meaning you can use them with any data type. For instance, if you want to sort a collection of descending order, instead of writing your own comparison function, you can simply use greater int. These built-in function objects are convenient and they reduce the need to write custom functors for common operations. This gives you more readable and concise code. While built-in function objects are useful, there are times when you need more control over the logic. This is where custom functors come in. A custom functor allows you to define your own behavior for specific tasks. For instance, here we have created a functor called isEven, which checks if a number is even by overloading operator. The logic is simple. It returns true if the number is divisible by 2 and false otherwise. You can then pass this functor into STL algorithms like countif, which counts how many elements in a container satisfy the condition defined by your functor. Custom functors give you the power to tailor algorithms to your specific needs. One of the powerful features of functors is that they can hold state. Unlike regular functions or lambdas that cannot store any data outside of their execution, functors can maintain internal data across multiple invocations. For example, in the counter functor, we track how many times the functor has been called by maintaining a count variable. When applied in an algorithm such as countif, it increments the count each time it is invoked. Stateful functors are especially useful when you need to maintain contextual information during algorithm execution or apply complex logic repeatedly across elements. Now let's talk about predicates. A predicate is simply a callable object, whether a function, lambda, or functor, that returns a Boolean value. Predicates are commonly used in STL algorithms where they help determine whether certain conditions are met. There are two types of predicates, unary and binary. A unary predicate takes a single argument and returns a Boolean, while a binary predicate takes two arguments and returns a boolean. Predicates are central to STL algorithms like COUNTIF, FINDIF, and REMOVEIF, where they define the condition or logic for comparison and filtering. Here's a practical example of a predicate in action. We use a lambda expression with REMOVEIF to filter out all negative numbers from a vector. The lambda acts as a unary predicate, returning true if a number is negative and false otherwise. REMOVEIF will then remove all the elements that satisfy this condition. This is a great example of how predicates give you the flexibility to easily customize STL algorithms with just a simple callable. Whether using function, objects, lambdas, or function pointers, predicates make algorithms dynamic and adaptable. It's important to distinguish between functors, function pointers, and lambdas. Each of these has unique features and advantages. Functors, as we have discussed, are objects that can store state and offer reusable logic. Function pointers are more lightweight and concise, but they cannot capture state or store data. Lambdas, on the other hand, are anonymous functions that can capture variables from the surrounding scope. The key difference between functors and lambdas is that functors are more reusable since they are full-fledged classes. Function pointers are typically used when you need to pass around simple function references. Knowing the differences helps us decide which to use in various situations. Now let's look at the real-world use case of functors and predicates. Functors and predicates are widely used in STL algorithms like sort, findIf, COUNTIF, REMOVEIF, and transform. For example, you can use a custom comparator in sort to order functions to order elements in a specific way, or use COUNTIF with a predicate to count how many numbers in a vector are greater than a particular value. By leveraging the power of function objects and predicates, you can write more expressive, efficient code. Functors and predicates are incredibly versatile tools that let us embed complex logic directly into our algorithms. It's time for some hands-on practice. First, try writing a functor called isPrime that checks if a number is prime. Next, create a functor named rangeChecker that accepts a minimum and maximum value and checks if a number falls within that range. Finally, use a custom functor to sort a collection and count how many comparisons it performs. These activities will help you solidify your understanding of functors and predicates and how they can be used to optimize your code. To summarize, function objects or functors are classes that overload the operator and behave like functions. They can hold state and be reused across various algorithms, offering more flexibility than traditional functions. STL provides many built-in function objects in the functional header for common tasks. Predicates are just callable objects that return a Boolean value and are heavily used in filtering and searching algorithms. Understanding how and when to use functors and predicates will make you a more effective C++ programmer, allowing you to harness the full power of the STL. Before we finish, let's do a quick review. First, what is a functor and how does it differ from a regular function? Second, which STL header provides the built-in function objects like plus, minus, and greater? And third, can you write a functor that checks if a number is divisible by 3? Take a moment to answer these questions and reinforce what you have learned today.